So let's talk more about this circuit that we've designed, which uses a thermoresistor, a temperature-sensitive resistor, inside a voltage divider. So we have here a voltage source. And we have two resistors, RF for fixed and R sub T, right? This is our sensor. And we measure the voltage across here. I'm going to call that again V sub T. And that's our design, right? And we've realized that V sub T is going to equal R sub T over R sub T plus R sub F times E. And so this equation here, which is the voltage divider circuit, tells us how the voltage will change as a function of these parameters. Great. Now, if you're using a thermoresistor, let's say this is our thermoresistor, right? That is one component of your design. And in the circuit, there are two other components. Yes?
I'm a little confused. Is RF the one that we touch, in order to measure the voltage of RT?
Great question. So the question is, right, the question is, in this circuit, are we touching the RF or we're touching RT? So in this particular example, we're touching RT, right? So RT is our thermoresistor. This is our thermoresistor. Resistor. It's a resistance that is a function of temperature. So this is the one. While this one here, we call it fixed. And by that we mean whatever value it is, it doesn't change, even if maybe the temperature changes. And so under that premise, the one that we want to grab is this one, right? Because if we grab this one, well, nothing's going to happen. So we grab this one, the resistance changes, and then the voltage changes, all right? Maybe a related question might be, could we swap the positions of these, right? Could we instead have made, so we talk about design, right? Let's talk about perhaps we had swapped and we made a circuit that looked like this. So this is E. I'm going to put the R sub T here, and this is R sub F, right? So I've changed the position between this one and this one, right? I've changed the position. And I decide that I'm going to measure the voltage here. Right? Would that have changed the performance? And the answer is no, because we can reapply the voltage divider equation here, right? And maybe a more general way to express the voltage divider equation is we start with the resistor that we're measuring the voltage across. Let's call that V sub T. And then we multiply by its resistance divided by the sum of the resistances. So that's going to be R sub T over R sub T plus R sub F. And then that's multiplied by the voltage. And so this equation, of course, ends up being the same as this equation. So that decision, now we would grab here, is not impactful. Good to know, right? Maybe obvious, right? But good to know as you're building these things. Okay? What if we measure the voltage here? So I'm going to call this V sub F. Is this still a useful circuit? Why might you do that? Maybe it's practical, I don't know, for whatever reason. Okay, let's think it through. All right, well, let's write the equation for the voltage divider for V sub F. We're going to say V sub F is equal to R sub F, because we're going to start with the resistor that we're measuring the voltage across now, over R sub T plus R sub F times E. Now, this equation is not this equation, right? And so what that means is that hypothetically, let's say if the temperature was 25 degrees, perhaps in this case, well, we know what we measured, right? Well, actually, in this case, it wouldn't matter. Let's say the temperature was 26 degrees. Try to be consistent, right? And in this case, we measured a voltage of, I think we corrected it to 6.7 volts, right? So in this case, when 26, and just out of curiosity, right? In this case, what was the voltage here? Right? What was the voltage here? Well, we know that voltage across F plus the voltage across T is equal to 10 volts, because that's what the voltage divider does, right? So the voltage across here in this case, based on that, would have been voltage equals 3.3 volts, right? So what happened was that this went to 6.7 volts and this went to 3.3 volts, right? This grew and therefore took more of the voltage, right? Well, I'm asking a very similar question here. Same circuit, right? I've changed the positions of these, okay? But I'm measuring the voltage here, right? And so in this case, when the temperature is 26 degrees, to write out values that we used previously, right, I would have something like 1 over, so in this case, right, this calculation came from something like 2 over 1 plus, 2 over 2 plus 1? Yes. So in this case, we're going to say 1 over 1 plus 2 times 10 volts. And so that's where we got our 3.3 volts. This situation is the same as this situation, right? I mean, when I'm measuring the voltage here. So it doesn't really matter how you build it. What matters is where you measure the voltage. And if you measure the voltage here, you get 6.7 volts. And if you measure the voltage here, you get 3.3 volts, right? But if you measure 3.3 volts here, you know what the voltage is here. It's the rest of it, right? Just like we did it here, right? So we could say that therefore, we know that, and this is VF. We know that VT is equal to 6.7 volts. So even though we measured the voltage here, we were able to then calculate the voltage here. I would then go from here, right. And if I know the voltage here, I know the resistance here. I guess it's a, I was doing a lot of extra steps here that were not necessary, okay? So we would start with this equation here. We measure this. This we know. This we know. This we know. All right, so this is also known. There's only one unknown. We make the circuit. We have all the information we need. We calculate R sub T, and then from R sub T, we would calculate the temperature, right? And in my opinion, there's nothing inferior about this approach versus this approach. From a design perspective, this is not inferior to that. I mean, the math, but you certainly have to be careful with the math. If you built this circuit, but you applied a different equation, you would get the wrong answer, right? So you need to know where you're measuring voltage, all right? All right. We're going to go back to this situation, right, where we built the circuit this way, and we're measuring the voltage here. But, you know, we can start thinking about R sub F and E. Because we inserted a 1 ohm resistor here, but we didn't have to. You could have put in a 10 ohm, right? We put a 10 volt battery here, right? A 10 volt source. Could have put a 1 volt, maybe even a 9 volt. So selecting these is part of design. Just like how you built the circuit, just like where you measure the voltage is part of design, selecting these parameters are up to you. Now you can say, I don't care, I'll just stick to 1 ohm and 10. You could, right? But then we want to ask the question, well, do these matter? If they don't matter, then they don't matter, but if they do, they do, right? Let's think first about the battery, right? So you'll notice in the example we had before, if at 25 degrees C, R sub T is equal to 1 ohm, then for, if RF is 1 ohm, right? This is the same example we had before, and E is 10 volts, then we get a voltage T of it was just 5 volts. Right? 1 divided by 1 plus 1 times 10, we get 5 volts, right? This was the example we had before. Let's go here and change the battery so that we're going to keep RF at 1 ohm, right? But you want to make a better circuit than everyone else, right? And so you're going to change this battery source to 100 volts. What would happen? Well, this goes from 10 to 100, right? This remains 1 over 1 plus 1. And so the voltage we would measure now is 50 volts. Is this a better device than this one, right? One person chose to power it with 10 volts. Another person chose to power it with 100 volts. Maybe the next person goes to 1,000 volts, right? Just keep bringing that voltage up and up. What is your sense? Same, better? Depends on the device.
I think it would be the same because the conditions that we have, the parameters are with respect to the resistor. So I'm thinking that if you change the context of it, but then at the same time, like, I don't know, that's my thought.
So I like to say about the context. In this case of move the problem forward, right? But typically, right, we're going backward. So let's say we don't know what the resistance is, right? Then in this case, we would measure 5 volts from our device. And because we have these parameters, you would then calculate 1 ohm. Okay. Now, let's say you measured 50 volts, right? Now, when you're measuring 50 volts, you can't use the same equation, right? In fact, you have to use the updated equation with the right parameters. But if you did that, of course, you would just get back to 1 ohm. So whether we started with a 10 volt source or a 100 volt source, once we've made the measurement and applied the correct equation to calculate back, in both cases, we would get back to the RT as equal to 1 ohm. And therefore, in both cases, we would be able to report that is 25 degrees C. And if the room warmed up, right, and this went to 6.7 volts, or this went to 67 volts, we would still be in the same situation where in both cases we would go back and calculate 2 ohms and therefore 26 degrees. So in the sense that I'm now describing it, right, it seems like both circuits work well, right? However, what is also clear is you need to know what E is. If you don't know what E is, then you're not going to be able to do this calculation, right? You have to know what E is, right? You always have to know what your parameters are. So it doesn't seem on the surface like there's much of a difference. However, we did talk in the previous class about how you would make a heating blanket, right? And how do you make a heating blanket? You take a voltage source, you connect it to a resistor, right? And you try to pump through as much current as you can, right? And then as the current goes up, you're going to produce more heating, right? This is the current. And so obviously the way you increase the current might be you increase the voltage, right? So when you're making a heating device, we want to use a particularly large voltage source, right? We want to make sure we're getting a lot of current through the system, and we want to know that we're producing heating. That's that application. Now in this case, that's going to be a bit of a problem. Imagine if we make a device that's designed to measure temperature, but it's heating. So then the question is, what are you measuring? Are you measuring your brother's temperature? Your brother touches it, he goes, ow, I just got burned, right? And you're telling your brother, oh, you're at 100 degree, not 100, you're at 100 degrees C. You're boiling. What's going on with you, right? Of course, it doesn't make any sense because we've made a mistake. So in this case, and again, these are arbitrary values, so I don't know how much it would heat up, but there is a risk when we apply too much voltage that we might heat up, right? It's also maybe a little bit harder to generate 50 volts than 5 volts for practical reasons, right? It's a little bit more voltage that you'd have to be able to provide, right? Like if you're doing this out of batteries, you would need to get quite a bunch of batteries and hook them up, right? If you were using 9-volt batteries, right, you need over 5 of them, right, to get to this voltage, right? And so there's also a practical reason. So this does matter for design. The voltage does matter. And in this case, we maybe are concerned with using too much voltage, right? Now, you could argue then, well, maybe 5 volts is too much, right? Maybe 5 volts is already too much. How do we know that? And so you may say, well, what I'm going to do is I am instead going to use, we'll put that scenario, we'll put it next to it. I'm still going to keep RF at 1 ohm, but my E is now going to be 0.001 volts. I'm going to play it safe. I don't want to make a device, because you realize if you're heating it, your device is not going to work, right? If you're heating it, you're done. I don't know what you're going to read, but it's going to be some weird combination of heating blanket plus sensors. You're saying, okay, so the safest thing for me to do is to go to a lower voltage. I'm going to go to,
Is that then related to the temperature coefficient?
We'll get back to that as well.
Sorry.
We'll get back to that as well, right? So the question is, does it relate to here? It will. That's what we're going to come back to. But let's talk about just using a lower voltage. All right. Let's move the problem in the forward direction. So it's as before, 25 degrees C, R sub T in this case, right? So now we sort of know the temperature, right? We have to know the temperature. R sub T becomes 1 ohm. We have our parameters here. And so what will we measure across the voltage here, right? Well, what we would measure is, given by this equation, 1 divided by 1, so it'd be 1/2 of this. So the voltage we would measure is 0.0005 volts, all right? Which is less than a millivolt. It's less than 1,000th of a volt, right? But, the math still works out. And conversely, if you had made this circuit and had you measured this voltage, you could have told me, oh, I know what that voltage corresponds to. That voltage corresponds to 25 degrees C. And if you had measured 0.0005 6, 7, you would have also been able to work it out. So the math doesn't break, but we're in a situation where we're not worried about the heating anymore. But there's another problem. You know, you have the practical situation that you're using a voltmeter, right? And the voltmeter doesn't have infinite sensitivity, right? It can measure 1 volt, 2 volt, half a volt, 0.1 volt, 0.01 volt, right? But at some point, the voltage becomes so low, and I'm not necessarily saying it's at this value, all right? But at some point, the voltage becomes so low that your voltmeter can't report it, right? Maybe you have to add a few more zeros here, right? But there is a concern that if you lower the voltage too much, right, you'll get to the point that whenever you try to measure it with the voltmeter, you will measure 0 because it's too low for the voltmeter to detect, right? And there's another reason we're going to get to as well related to noise as well, all right, that we're going to come to later. So while this seems very appealing, I'm going to flag up right now that this is not without consequences as well. However, the consequences of doing this come up in the real world. They don't come up in the math. Okay. We've played around. So we have our circuit here, right? This is our circuit. And we have a voltage source and a fixed resistor, right? And our thermal resistor. And we've built it this way. And we've considered the impact of how much voltage we put here. And maybe we're kind of thinking there's a little bit of a Goldilocks. Too much may not be good, too little may not be good. So there's a certain amount that we need to use in order for our circuit to be successful, right? A bit unclear what that is exactly, right? But we understand that you need to find the right voltage in order to make it work. What about RF, right? That's something else that we started with. We picked 1 ohm. Could have picked 2 ohms, could have picked 10 ohms. And you could ask the question, as we did with the battery, does it not matter? So just pick whatever, or does it matter? So let's consider that next. We're going to start with the same example here. Only now, what we're going to do is we're going to alter the value of this resistance. And so let's go ahead and use the example. Let's say you chose to use a 1 kilo ohm, which is a 1,000 ohm resistor. What voltage would we get? Well, we can calculate that. We need to go back to our voltage divider circuit, but we need to be aware that this parameter here has now changed, right? The voltage remains 10, but this parameter has changed. So this is going to equal 1 ohm divided by 1 plus, we'll write it out, 1,000 ohm times 10 volts, right? And now let's do this calculation exactly. Someone do it. 1 divided by 1,001 times 10, what do we get? One divided by 1,001 times 10? 0.0099 volts. A very small voltage, right? And on paper, that's not a problem, right? However, we express some concern about being able to measure very, very small voltages with our multimeter. Okay. If the temperature went to 26 degrees, let's consider this example. Now the temperature is 26 degrees. We know that when it goes to, let's say when it goes to 26 degrees, to keep things simple, I'm going to say that RT goes to 2 ohms. So the room has warmed up. In this case here, what would we measure? Well, this is no longer 1 ohm, it's 2 ohms, but we have 2 ohms, 1 ohm, 10 volt. And as we've done before, the voltage we're going to measure now is around 6.7 volts. And so when the room went from 25 degrees to 26 degrees, right, the temperature the voltage we measured went from 5 volts to 6.5 volts, right? Pretty clear reading, right? 5 volts, 6.5 volts. I know something's going on and I like what's going on. What would happen in this situation? Well, in this situation, we would now be in a situation where we are at 2 ohms over 2 plus 1,000 times 10 volts. And again, someone do that calculation. How much would we measure in this situation? So 2 divided by 1,002 times 10. 0.0199. Now, in principle, right, this value is certainly different than this value, right? But in absolute terms, there's been a very small change, right? The change from here to here, the delta, right, was 6.7 volts minus 5 volts. So it was 1.7 volts change, right? This was the delta, right? Well, the delta here, if you were, right, would be 0.01 volt. So for the same change in temperature, in the one case, our voltmeter moved from 5 to 6.7, which was a 1.7 volt shift change. In the other case, where we had decided to put in a 1 kilo ohm resistor here, we started with a very, very low voltage, right, somewhat low. It did change, right? But in absolute terms, it changed a very small amount. Now, as far as paper calculations, neither one of these appears superior or inferior, just like changing the batteries didn't seem to make a difference, right? But in reality, right, there is a limit to what you can detect with your voltmeter. And as we've also talked about, there's going to be something called noise, right? That's going to make things a lot harder for us. And so while on paper, both of these things seem to work, in practice, this one is very much preferred. Not only are we working with larger voltages to begin with, right? But we're producing bigger changes in voltage. Whereas in this case, right, and remember, in both these cases, the voltage was 10 volts, right? But because of the resistance that we chose here, this happened. Now you could take this to a more extreme level. Instead of a 1 kilo ohm, you could have chosen 1 mega ohm, right? 1,000,000 ohms. And you could have replugged in these values, right? And you would have gotten you would have gotten even more zeros. Now, would the math still hold up? The math still would hold up. But you would be talking about even smaller voltages and even smaller changes. And so we've reviewed how you can make this circuit, right? And you can choose this parameter, and you can choose these parameters, right? That's part of your design. And it turns out, here we went big, right? It turns out that if you went small, you might see similar issues as well. So we have a sensor and we have a circuit. And I would say that we want to design the circuit so that when the sensor changes, parentheses, because, to write it out, whatever, the thing we are measuring changes, the output, which I'm going to call voltage, of the circuit changes as much as possible. A little bit wordy. Well, that's what we're going to say. You are deciding how to build this circuit. You are deciding what elements to put into it. And you can make good decisions and you can make bad decisions. Now, in this case, the decisions are kind of limited, right? I mean, there's only 3 elements. So there's how you connect them, where you measure the voltage, and the parameters that you pick. But what we have seen is that depending on the voltages that you pick, depending on the resistances that you pick, there will be certain consequences, right? We saw that you have to be sensitive to the voltage, because too high of a voltage, you're going to get into technical issues and heating. But if you do too low a voltage, you're not going to get that much of a change. It's still going to change mathematically, but not much. And we also saw that with the resistance, if you pick a resistance that is too high, you will once again be in a position where the voltage that is being produced by the circuit, right, is not very much, and not changing very, and more importantly, not changing very much.
So you need enough of a change that is detectable, but not so much that it throws off your results. Like if you have too much heat, too much change to the system, it'll interfere with your reading.
Too much change is usually not a problem. It is in that specific case where we talked about using excessively high voltages, but there I think it's an issue. It's a challenge for another issue. Usually what we're doing is we're trying to do everything we can to produce as much change as possible.
So I'm wondering, you said there's some good decisions and bad decisions. I'm not sure which one this is yet, but
Yeah.
we know there's like a sort of range for the thing we want to measure. Like humans can only be so many temperatures.
Yes.
Right? Does that at all help us to narrow down like what values we can use?
So knowing that human beings are going to be in a certain temperature, right, is going to tell us how much this temperature is going to vary, right? It's going to tell us that this isn't going to be any lower than X and any higher than Y. And so that also gives us a range of how much this resistance will change. And that actually is the basis for actually how we would optimize RF specifically, right?